Okay, so yesterday we said whenever we're comparing two relative acids to one another and determining which one's more acidic, the simple thing to do is to write out a simple acid-base equilibrium reaction and then look at your conjugate base and ask which of the conjugate bases is more stable. And we came up with this mnemonic called cardio, where we look at the charges first, atoms second, resonance third, dipole induction after that, and then orbitals last. So in the first example, we said, all right, if we compare the conjugate base for hydronium to the conjugate base of water, water on the right-hand side doesn't have a charge, therefore it's more stable than the one with the charge. That means hydronium's a stronger acid. And then we got into atoms after that, and we said, all right, what if they both have a negative charge and we're tied in that charge category? If we're comparing two atoms that have a charge and they're in the same row, the one that's more electronegative is going to be more stable. Therefore, in this case, water is the stronger acid. With atomic size, we're comparing two atoms with the same charge that are in the same column. So in this case, iodide is much bigger than chloride. It's more stable, which means hydroiodic acid is stronger. Then after that, we go to resonance. Conjugate bases that have resonance are a lot more stable. So in this example, the carboxylic acid's more acidic. Then we saw dipole induction. In this case, there was no resonance. Charges were on the same atom. Everything was tied. But the fluorines that were attached to the molecule on the bottom were tugging on the negative charge. That made it more stable. Then we said this really depends on proximity of the negative charges. Typically, dipole induction drops off with distance pretty dramatically. I can't remember if it's r to the fourth or something like that, but it's a big drop off. And then last but not least, we looked at orbitals. We said if you have a negative charge in an sp orbital, it's closer to the nucleus. That means it's more stable than if it were in an sp3 orbital. There are exceptions to this, though. These are just general guidelines, so I'll show you the most common exception. And I think this is one you might run into in sapling, which is why I'm bringing it up. So let's take the following example. Let's say we have ammonia, and we treat it with some sort of base. That means we're going to treat ammonia as the acid in this situation, right? Because B just stands for base. If I do that and pluck a proton off, that means that this nitrogen would then have two lone pairs, two remaining hydrogens, and a formal charge that is negative, plus our conjugate acid right there. And let's compare this to a second completely different molecule. We'll do acetylene again. And with acetylene, you can pluck off one of those protons off of one of the terminal carbons. That gives that carbon a negative charge, and we end up with our conjugate acid. All right, if we go through the cardio rules, we're comparing this conjugate base to this conjugate base. Both of them have a -1 charge, so we're tied at that charge level. Then we go down to atom. All right, which one do you think would be more stable according to the atom rule? Nitrogen, right? Nitrogen's more electronegative than carbon. Intuitively, we would think, shouldn't that one be more stable than the carbon with the negative charge? No, it's a weird exception. So if we look at this one, we'd say we would expect this to be more stable due to electronegativity. However, that's simply not true. It is more acidic. The reality is nitrogen isn't that electronegative, and in this case, orbital hybridization is more stabilizing than nitrogen having the negative charge. Like I said, the cardio rules are just general guidelines. They work about 90-ish% of the time, but there's those weird examples that might bend the rules a little bit. Does that make sense? All right. So today what we're going to do is kind of an offshoot of what we did yesterday, and we're going to focus on identifying the most acidic protons in one molecule. And the simple trick I'll show you is when in doubt, Draw all possible conjugate bases. And then compare all of them. Okay, so let's do this one first. So identify the most acidic proton. And I'm going to color code them. I really like color coding these. And we'll do it this way. I'm just going to put R groups on here. Off of the left carbon up here, I'm going to have a red proton. And on the right, I'm going to have 3 blue protons. So essentially the question is, which is going to be more acidic, the red proton or the blue proton? Meaning, if I were to treat this with a base, which proton would get removed first, preferentially over the other, the red one or the blue one? So let's try this. It's always good to argue, at least in a classroom, maybe not in Washington, D.C. So we'll do minus the red proton first, and draw the conjugate base for that. That means all of the blue protons are staying put. That means the central carbon is going to have a negative charge, and there we go. All right, now we'll do the opposite one and remove the blue protons, and I'll do that going a different direction. So I'll write minus the blue proton. Oops. And we'll draw the conjugate base for that one. And that means the carbon on the far right-hand side has a negative charge in this one. All right, if we look at both of these, we could say, all right, we've drawn out all possible conjugate bases. Does it matter which of the blue protons I took? No, they're all equivalent to one another. All right, we go down the list and we'd say, all right, is one containing a different charge than the other? No, they're both -1, right? Then we go to atom, we'd say the negative charge is on a carbon in both of those, so we're tied at the atom level. All right, after that, what's next? Resonance. All right, so let's focus on this one. Is there any resonance that we can draw? Well, let's try, right? Let's assume I try to move this negative charge to be down here and form a new pi bond. Is that okay? No, that carbon already has an octet, right? If we form a triple bond there, that carbon on the left would have 5 bonds. That is not allowed. All right? Conversely, we can say, well, what if we move it that way? Same thing, that carbon would have 5 bonds. So this one has no resonance in the top right-hand corner. Let's try the bottom one and say, all right, what if I move that there? Now that central carbon has 5 bonds. Can we fix it? Yeah, we can break this pi bond and shuttle the negative charge all the way over to the left carbon. So this one has a resonance structure. And we'll draw in all of our color-coded protons, but this time the negative charge is located down there. All right, so really quickly, looking at this, we can say, well, if we remove one of the blue protons, we have a resonant stabilized conjugate base. That's more stable than if we were to remove one of the red protons. Therefore, the blue proton must be more acidic, right? So let's make a note of that. The blue protons must be more acidic since the potential conjugate base is more stable And like we said, this was due to resonance. Does that make sense? It's really easy in this case. We only had 2 potential protons to look at. But let's try one that's a little bit harder. We'll gradually work through. So for this one, I want you to determine where the most acidic protons are on ethanol. And then explain why. Actually, let me color code this. I've got a green proton here. I've got 2 protons coming off the CH2 portion. And I've got 3 of them coming off the CH3 portion, so I'll color code those as red. All right. Which proton type do you think is going to be most acidic? The red protons, blue protons, or green protons? And check with your neighbor and see if you agree. If you agree with your neighbor, give me a thumbs up. If you feel pretty confident, give me a thumbs down. If you're lost, a sideways thumb if you're kind of not sure. I'm not seeing very many thumbs. A few sideways thumbs, a few thumbs up, a few thumbs down. All right, so I'll show you how I would go about doing this. So in the first example, let's just choose a red proton. I'm going to remove that and say, all right, negative charge there. That would be a negative charge on a carbon, right? Okay, let's put that back and say, all right, we know one of the potential options would be to have a negative charge on a carbon. Let's do this one. If we remove that proton, we'd have a negative charge on a carbon. Okay, we'll keep that in mind. Add it back in. And then over here, if we were to remove that proton, we'd have a negative charge on an oxygen. All right, so it looks like we're narrowing it down, right? So one option is to have a negative charge on one of the carbons. The other option is to have a negative charge on the oxygen. Which one is going to be happier? Negative charge on an oxygen or a carbon? Oxygen. Why? Electronegativity. Yep.
It's kind of a little bit off topic, but we should be able to check this using some equivalency between bond length and joules and checking the energy of the...
So you were asking about looking at bond dissociation energy? That's a good question. So bond dissociation energy is different. That's called a homolytic cleavage. So one electron goes to each atom. That's different than plucking in a proton off where both electrons go to one atom. So they're different than one another. But in general, this sort of guideline works really well. Like we said, this one is most acidic. Since the negative charge would be on the more electronegative atom. So sometimes you can go through these really quickly in your head, no problem, find them pretty quickly. But I'll give you some more challenging ones, because I know everybody likes a challenge. Yep.
Would the blue one then be the second most acidic, because you have resonance structures that you can make off of it?
So the blue one, if you remove one of the blue protons and you have a negative charge there, there's actually no resonance structures that you can do without violating the octet rule on one of those atoms. So there's no resonance in any of these potential conjugate bases. Let's try a harder one though. All right. We've got this hexagon with the nitrogen in there. This nitrogen has a lone pair. And I'm going to narrow down the protons that we're going to look at. We're going to look at this proton over here in blue, these protons down on the bottom in green, and we'll compare these to the red protons up here. Question is, which of these are the most acidic protons and why? So I'll give you a minute to check with your neighbor and see if you agree. All right, so let's go through this together. What I've done is I've just made a skeleton structure just to speed things up as we go through it. So in the first one, we removed one of the red protons. We still have one red proton left over. We still have this blue proton, and we still have both of these green ones. Where's my negative charge supposed to be? Top carbon, that's where we removed a proton, so it's right there. Okay, so that looks pretty good to me for a negative charge and a conjugate base. All right, next one down, we removed the blue proton, so there's nothing coming off of that carbon. And we have 2 green protons right here, 2 red protons here. And where's our negative charge supposed to be? Yeah, the carbon below the nitrogen, the exact spot where we removed the proton, right? So I'll go ahead and draw the conjugate base for that one. All right, and then last but not least, we're going to remove one of the green protons, so we still have our blue proton left. We still have 2 of our red protons, and we still have 1 of our green protons. All right, negative charge is now down here. Like I said before, it doesn't matter how many protons are coming off of a given carbon. Just imagine removing 1 of them. The number of protons doesn't impact anything. Okay, so now that we've got our conjugate bases drawn, we've got to determine which one's more stable. So if we look at all of these, they all have a -1 charge. So we're tied at that charge category. Next, we go to atoms. If we look at the top one, we've got a negative charge on a carbon. Next one, down, we've got a negative charge on a carbon. Bottom one, negative charge on a carbon. We're tied. All right, so after atom, we look at what? Resonance. So let's try to find resonance structures. So for example, I've got this negative charge. Can I form a pi bond right there? Well, if I do that, I have over an octet, but we can fix that. Say, hey, I can move those electrons over there. Oops, no more pi bond, excuse me. So we still have this red proton right here. We still have 2 green protons. We still have this blue proton, but now the negative charge is located over there. Are there any other resonance structures? I don't see any. So we'll go ahead and close this off with brackets. Let's double check the other ones though. All right, the one right below it, we've got a negative charge. Can I move these electrons down here? Nope, otherwise we have a Texas carbon. All right, can I move these electrons right there? Nope. Otherwise we have a Texas nitrogen, and there's no way of fixing that Texas nitrogen in this situation. So this one has no resonance. So we'll just make a note here, no resonance. All right, and then the bottom one, let's try this. Say, okay, this negative charge, let's try moving it this way. All right, if we do that, now we have a Texas carbon, that carbon where the blue proton's coming off. Can we fix that though? Sure, why not? Can move the negative charge up to the nitrogen, right? Okay, so let's draw the resonance structure. Everyone's looking at me and scowling. Like, what is going on right now? Why are you doing this to me? I should have just been an English major. But I don't like reading. All right. So here we've got our resonance structure for this one. Looks reasonable to me. We've got a negative charge on the nitrogen. Whoop, I'm missing my double bond right there. That's why I keep everybody around. Yep. So, not exactly. You would have to move the electron, then break a pi bond, not both at the same time. I think I'm understanding your question. So your question was, why can't you just kick this up and then kick the pi bond down? Or the lone pair?
The lone pair goes to the blue hydrogen, go down, and form a pi bond.
Right here? This way then? So if you do that, then the bottom carbon has an octet, or more than an octet. Yeah, so it is tricky. I always recommend drawing all the resonance structures and then cross out the ones that have Texas carbons just to remind yourself these are not valid. All right, so now we're in this tie, right? We know the blue proton's definitely not going to be the most acidic proton. It doesn't have any resonance. But the top one, meaning removal of the red proton and removal of the green proton, both have resonance. So now what do we do?
You suffer.
Well, let's look at the resonance structures, right? And we have to think about them in a bit more detail. In the first one, the negative charge is shared between two carbon atoms, right? The bottom one, the negative charge is shared between a carbon atom and a nitrogen atom. Ooh. Now what do you think is the most stable? Yeah, the carbon-nitrogen one, right? So again, we're kind of defaulting back to that atom rule because we need to look at where that negative charge is located, which atoms it's on. So in this one, we would say, all right, this one is more stable since the negative charge is shared between a carbon and a electronegative nitrogen. So the nitrogen in this case did make the difference. Like I said, this is not intuitive. Oftentimes you have to draw out the conjugate bases step by step, look at the stability by drawing out all the potential resonance structures and so on. That's why I said if you don't understand resonance, it makes a lot of this stuff super challenging, and it kind of limits your ability to analyze acid-base problems. All right, let's do a more challenging one. Yep.
So what if you have a point where one has like 3 resonance forms, but a different one has 2 resonance, but it's on like oxygen has a negative, so it's like 3 carbons having a negative, or 2 oxygen having a negative.
Okay, so the question was a hypothetical question asking about, all right, what if you're comparing one conjugate base that has 3 resonance structures versus another potential conjugate base that has 2, but the one with 2 resonance structures has delocalization across an electronegative atom where the other one doesn't? It can be hard to tell in that case, and I would refer to a pKa table. Yeah. All right, so let's do a harder one. All right, so for this one, we're going to look at a fused ring system. So it's 2 hexagons that are linked together. I think this might have been off of an old exam. All right, bear with me. All right, we've got a blue proton off this position, green protons coming off that position, and we'll add in 2 red protons over here. Let's determine which of these proton sets is going to be more acidic. Is the red proton going to be most acidic? One of them? Is the blue proton going to be most acidic? Or is one of the green protons going to be the most acidic? All right, let's try to do this as a class just for the sake of time. There's other stuff we need to cover today. All right, so let's imagine we remove a red proton. So I'll just use my eraser here. If we remove that red proton, those electrons must be off of that carbon. Makes sense? All right, let's say we remove the blue proton. That's the middle column. So I'll remove that proton. We would now have a negative charge there. All right, and last but not least, let's imagine removing one of the green protons. So I'll just remove one of those, and we would have a negative charge on that carbon. Make sense? All right, so we go through the cardio rules. It's -1 versus -1 versus -1. We're tied at the charge level, right? Then we go to atoms. And we'd say, all right, negative on a carbon in the first column. In the middle column, negative on a carbon. Last column, negative on a carbon. So we're tied at the atom level. After that, what do we look at? Resonance. So let's focus on column 1, loss of the red proton. And with this one, we can take this negative charge, move it there. However, we would run into a Texas carbon problem. How can we fix that? Yeah, move the pi bond to the oxygen. Okay. So now we can go ahead and say paste. Let's clean this up. So when we do this, we're going to have a red proton there. We're going to have a new pi bond down here. Negative charge is now on this oxygen. All right, are there any other resonance structures that we can draw? I don't think so, without going backwards to our original structure, right? So if we think about loss of a red proton, I'd say we're pretty limited to these two resonance structures, but that's okay. Let's try the blue one. And we can say, okay, with the blue one, are there any resonance structures? Well, let's try. Which way do you want to move the negative charge? Left or right? Left. Okay, so I'll try moving that left. All right, if we do that, we'd have a Texas carbon. So let's try breaking that. Kick it up to the oxygen. Same sort of idea as before, but let's take a look at this structure this time. Okay, so we're going to move this negative charge over here. Whoops. Let me change these to regular electrons. We don't have this blue proton anymore in this structure. We have a pi bond there. We have a pi bond there. All right. I see students draw this a lot as a possible resonance structure. I will say that it's incorrect. Does anybody know why? Give you a hint. Let's zoom in on this a bit more. Right? Think about this carbon right there. What's the hybridization of this carbon? sp. What's the preferred bond angle for an sp hybridized carbon? 180. We're forcing it into about 120. That's not a happy looking bond angle. So I'd say it wants to be 180. Therefore, I'm going to put a little frowny face here and put an X through it and just say this isn't really a valid resonance structure, because in order to accomplish that, we'd be contorting it so far out of Vesper alignment, it's just really not going to occur. Make sense? All right, now let's do the last one. We can try doing resonance. And if we look at this one, I could say, all right, let's move this over here. Now we have a Texas carbon. That's okay. Move that over there. Oh, another Texas carbon. That's okay. Can move that over there. So let's plug this all in. And we'll draw our new structure. Okay, our new structure has a pi bond right here. We still have one green proton coming off of there. We have a new pi bond over here, and the oxygen has a negative charge, right? All right, we can even go through intermediate structures if we want. So for example, maybe I could kick this electron back down and kick this electron onto that carbon. So we could be super thorough and show all of the possible resonance structures. So let me go ahead and draw this in. Okay, if we do that, this pi bond's still in its same spot, and we have a negative charge right there. All right. So now we've got, I think, all possible conjugate bases with all possible resonance structures drawn. Now, going back to our original question, now that we're exhausted and forgot about it, which proton's more acidic, the red proton, blue proton, or green proton? Green. Why? It's got more resonance structures, and one of its resonance structures allows it to delocalize to an electronegative atom. So not only does it share that negative charge with an electronegative atom, it's distributing that charge across 3 total atoms. Does that make sense? So this one's more stable. Because it has more resonance structures. Oh. All right, so I know this does get pretty tricky. I would encourage you to practice these book problems. They take a while to get good at. They are tedious. Don't be afraid to go slow and make mistakes. All right, there's one last thing we wanted to talk about that you might need for the pod, and that's selecting an appropriate base. If you have that common bases handout that I gave you, you might want to pull that out. But again, I'm going to redraw the generic acid-base reaction and say, all right, we've got a proton of interest that we want to deprotonate. I don't want to deprotonate any other protons. what base might I need to accomplish this? All right. And like I said, you can always think of this being a competition between your original acid and your conjugate acid. And I'm going to phrase this another way. If we want to favor deprotonation, what should be the stronger acid? The acid or the conjugate acid? It's kind of weird to think about, right? We said the stronger acid pushes the equilibrium to the opposite side. We're saying we want to deprotonate our original acid and make A minus. That means our original acid should be the stronger acid, right? It sounds kind of like we're talking in a circle, but it makes sense, right? If we want to favor deprotonation, our original acid must be stronger, i.e. lower pKa, than our conjugate acid. Seems really simple, right? If that acid that we're starting with is stronger, it's going to push the equilibrium towards the product side. Okay, so let's take an example of this. And I'm going to use acetylene. And I'm going to use some generic base. Looks like this. And I want this to ideally be a one-way arrow. Although let's just be consistent with how we've always drawn it and show it equilibrium arrows. And this base is going to come deprotonate it. We really want to deprotonate this and form our acetylide anion. All right, so first thing I would always do is look up the pKa of my acid of interest, or find something that's approximately close to it. So in my pKa table, I'd say, all right, the pKa value I find for this is about 24. What does that tell you about our conjugate base? Should the pKa be higher or lower than 24? Higher than 24. So should be higher than 24 if we want the deprotonation to be favored, right? Okay, so let's find an example of this. Okay, in this first example, we're going to use hydroxide. That's the base you used a lot in Gen Chem. Okay, in this one, same reaction. So now we have our acetylide anion. Like I said, the pKa is 24 for this. Does anybody remember the pKa for water? 15.7. Will this be an appropriate base for deprotonating the acetylide ion? No. So this is a poor base selection. Because this pKa is lower than the original acid. All right, so on the sheet that I gave you, yep.
Can we also look at it, like if we don't do it with pKa, can we do whichever one has the more stable base, or like if the conjugate base or the regular base are more stable?
You can make some educated opinions, but I always like doing pKa's if I can. So what I did for you was I gave you a pKa table, and I gave you bases and their corresponding conjugate acids, right? So in this example, we want our conjugate acid to have a pKa greater than 24, preferably by a few orders of magnitude, right? All right, so if we look at this, what might be a better base to use for this deprotonation? Yeah, we need something greater than 24, so nothing in the left-hand column will work. Maybe let's use sodium hydride for this reaction. So in this one, we could say, all right, we take the acetylide anion and we take sodium hydride. You don't even need to show sodium, it's a spectator in this case. So the hydride base will grab this proton, and we could say, all right, in this situation, we made our acetylide ion. What's the conjugate acid going to be? H2, which is pretty convenient as a chemist because H2 is a gas. It's going to bubble out of solution. We said the pKa is going to be 24 here. pKa of hydrogen gas is what? 36. So this would be a much more appropriate base. It's got a significantly higher pKa for the conjugate acid than of the original acid. So that's the second half of the pod that I want you to work on. And then tomorrow, when we come back, we'll talk about solvent and do more practice.